Please welcome to the stage Marcy O'Malley, Session Chair. Stand by.
Good morning. It is so great to see an audience like this at 8:30. I hope you're looking forward to another great day of ICRA 2022. It is my pleasure to introduce our speaker for this morning's session. Julie Shah is a professor of aeronautics and astronautics and associate dean of social and ethical responsibilities of computing at MIT. She directs the Interactive Robotics Group, which aims to imagine the future of work by designing collaborative robot teammates that enhance human capability. She's expanding the use of human cognitive models for artificial intelligence and has translated her work to manufacturing assembly lines, healthcare applications, transportation, and defense. Before joining MIT, she worked at Boeing Research and Technology on robotics applications for aerospace and manufacturing. Professor Shah's contributions have been recognized at all stages of her career progression. She has received the National Science Foundation Faculty Early Career Development Award and was recognized by MIT Technology Review on its 35 Innovators Under 35 list. She was also the recipient of the 2018 IEEE Robotics and Automation Society Academic Early Career Award for contributions to human-robot collaboration and transition results to real-world applications. As evidence of the breadth and impact of her work, she has received Best Paper Awards and nominations from multiple societies and conferences, including the ACM IEEE International Conference on Human-Robot Interaction, the AIAA, the Human Factors and Ergonomics Society, the International Conference on Automated Planning and Scheduling, and the International Symposium on Robotics. She's also, in her free time, an author, co-author of the book, What to Expect When You're Expecting Robots, The Future of Human-Robot Collaboration. I'm sure with that introduction, you are now all expecting an amazing keynote to kick off day 2, and I'm certain you will not be disappointed. Please help me welcome to the stage Professor Julie Shah.
Hi there. So I'm Julie Shah. I'm an AI researcher and a roboticist, and I focus on developing machine intelligence that enables more seamless collaboration between people and robots. My work, my lab, focuses on developing collaborative robots that work alongside people to build planes and build cars. We also develop intelligent decision support for other experts, like nurses, doctors, pilots. We work on making robots and machines more effective team members. And good teamwork is good teamwork, whether it's in an operating room, whether it's in a cockpit, or whether it's in a kitchen cooking a meal with your partner. So the vision behind my lab's work is to be intentional about developing computing and robotics that augments rather than replaces human capability. Now, you might look to the latest news articles and studies, in the US at least, and see a very different vision for our future. There's been increasing unease and concern about the growing role of robotics in manufacturing and other sectors and its relation to human work. Some worry that our technologies will reduce opportunities for the next generation. I have a 3-year-old and a 5-year-old, so I care very much about this. But for many, a generation can seem far off. Other sources contend that this future is already here. These are what we call top-down studies looking at macro trends that provide evidence that robots may already be supplanting our jobs at a very fast clip, that one industrial robot may be eliminating 6 jobs in a community. So if this is where we are today, let's just roll this out a little bit and take a few steps into the future, and it quickly leads us nowhere good. It leads us to Judgment Day. So, yikes. At least we can all start by agreeing that this future is not desirable. In 2018, MIT's president, President Reif, convened an interdisciplinary task force of researchers at MIT to investigate these claims and to identify what we could do about it. My lab and I had the pleasure of working with new colleagues in the social sciences, and the picture that the task force uncovered is much more nuanced and complex. The research suggests that the problem is not robots taking people's jobs, but that the problem is actually the opposite. Only 9% of manufacturers even have a single robot, and most of the robots are concentrated in a few very large firms, so for example, automotive and electronics. In a time of need during the pandemic, fewer robots were purchased, And half of the users of industrial robots are actually low users. They don't even use the robots they have that much. The task force found that these top-down studies looking at these macro trends are misleading. Technological change is replacing existing work, but it's also creating new work. And exactly how it's doing that is very context dependent. So bottom-up studies looking at the details of what's happening in particular firms tell a different story. So let's look at this. Here's a plot showing capital expenditures per employee over time. Capital expenditures are technology investments. And you can see the plot here goes from the 1950s to near current day. That red line on top is large firms. The blue line on the bottom is small firms. The green line is medium firms. Small and medium firms are firms that represent those with less than 500 employees. So you can see the acceleration in the investment in CapEx and technology for the large firms, especially in the last few years. And you can see the widening gap between the investments of these large firms and these small and medium firms. Now let's look at wages, payroll per employee over time over the same time frame. Again, we can see on the red line, large firms significantly lead with a widening gap between those large firms and those small firms represented by blue and those medium firms represented by green. So that's technology investment, wages, and now let's look at productivity. Again, we see a trend of increasing productivity of these large firms and small and medium firms falling behind. So you might ask, how many small and medium firms are there? Is this really a significant deal in terms of the bigger picture? So these small and medium firms, they represent 98% of all manufacturing establishments in the US, and they employ 43% of all manufacturing workers. The technological upgrading of firms is directly linked to their competitiveness, and these small and medium firms are falling behind on all these measures. So there's deep scholarship on this. But for the Cliff Notes, something that's suitable for a non-social scientist, great for inclusion in your teaching, you can find this excellent short read titled The Puzzle of the Missing Robots, published as a part of the MIT Case Study series in Social and Ethical Responsibilities of Computing. So the case study and scholarship describes exactly what we see in those charts. It's a crisis for small and medium firms. It's what our colleagues, Suzanne Berger and Ben Armstrong, coined the low-tech, low-skill, low-wage equilibrium. So firms are not utilizing the latest technologies. They lack the skills to use these technologies, and they also see low wages. Upgrading of skills translates into upgrading of wages. Upgrading of technologies translates into upgrading of skills, but they don't have the technologies or the skills to break out of the zero-sum situation. So it's a stalemate. The case study points out the obvious concerns over firms' competitiveness, but there's also clearly massive economic inequity here. So now what's happening to those few firms that are adopting robots? Are they losing jobs? So nope, that's not true either. Technological change is replacing existing work, but it's also creating new work. And exactly how that's happening, again, is very context dependent. So these bottom-up studies that are looking at details of what's happening in particular firms in particular countries see a variety of things. In some cases, firms employ more workers after robots. In some cases, they employ fewer workers overall. So for example, in France, in large firms with international markets, they employed more workers after robots were introduced. But in that same country, their domestic competitors lost workers. In studies from Canada, Germany, and the Netherlands, these show changes in workforce composition. So for example, a study in Canada showed that the introduction of robots actually led to a reduction in the number of middle managers, but actually an increase in the number of production workers. In the US, we see examples of firms that adopt robots and then offer higher wages, but offer fewer jobs overall. So these technologies are not deterministically leading to one future, but to many possible futures. Some firms were more productive and saw increases in wages and job opportunities for technicians, and some did not. This evidence reinforces that the urgent problem might not be that robots are taking people's jobs, but it might be that robots are not doing the job for us that we need them to do. So now let's switch over and talk about the capabilities and limitations of industrial robots. So as I see it, we have three eras in robotics for manufacturing that characterize the relationship between humans and robots. So era one is what I'll call don't go there. That's manufacturing robots are unwieldy, they're unsafe, they're locked away. People are not allowed to enter that space. Era 2 is what I call get out of the way. So the robots are freed from their cages, and humans and robots share space but coexist uneasily, and the choice is zero-sum. Era 3 is the topic of this talk, so it's the alternative to the zero-sum. And I represent this third era with a question mark because how we shape this third era is up to us. I'm going to discuss, in my view, what I see as what is needed to move us from a zero-sum paradigm to a positive-sum paradigm that enables us to harness the relative strengths of humans and robots to accomplish what neither can do alone. So era 1, robots are locked in cages. There are certainly winners and losers with this approach. Manufacturers with high volume, the ability to standardize work with long runs, automotive, for example, was able to really make use of these era 1 industrial robots. But other more complex and dynamic settings, like the work done in aerospace assembly or the work done in these small and medium shops, these are settings where there's no fixed tasking, at least not the type you can program for a robot. Small and medium firms tend to have high mix, low volumes. It's much easier to tell a person how the job changes from day to day or even hour to hour than a robot. And as a result, in sectors like aerospace and these small and medium firms, they were not able to find a way to make practical use of these systems. So between completing my PhD at MIT in 2010 and starting on the faculty there the next year, I had a unique opportunity to work out at Boeing on robotics and automation for the building of large commercial airplanes. And I hadn't set foot on a shop floor before, and it was truly inspiring. So every day at 10 a.m., I would pause and look up as another portion of a tail section was installed on a new 737. Assembly of the aircraft was primarily manual. It was a beehive of activity. Every day required workers to bring their best to work in a team to achieve an incredibly complex feat. And I learned firsthand out at Boeing the challenges of automating in these more complex settings, that it wasn't a matter of getting the physical work done, but that success relied on people and teams to be creative, adaptable, and flexible. So the challenge of these first era robots, these cage systems that entirely remove people from the equation, you're making a very significant trade. When you're able to, if you're the type of firm, you can trade an increase in productivity for a substantial loss in flexibility. And a few types of firms could do that. But with very high switching costs, many were locked out of using these systems, like aerospace and small and medium firms. So era 2, so this was the beginning of my career. It was incredibly exciting because we were able to do something different. In 2012, I showed up at BMW, and we began working on developing robots that could be safely freed from their cage to augment human work on the final assembly line. My lab focused on developing the AI that would enable robots to work more flexibly with people, to share space safely and efficiently. And the goal of my lab's work over the past 10 years has been to make robots smart enough to work with people. That means smart enough to maneuver freely, like a freely mobile robot, for example, out on BMW's automotive assembly line. Smart enough to coordinate shared workspace with a person, to see a person as more than an obstacle, but to see them as someone who has tasks to accomplish and to be able to anticipate what they'll need and not get in the way. And then to actively collaborate, to work interdependently to offer the right material at the right time. So I'm going to illustrate what these types of new technologies enable and how it changed the state of the art in assembly. So I'm showing you here a facility out at BMW where there's an associate that needs to be able to access, as a part of their work, the shared region in which the robot, in this case a universal robot on a rail, is working. And the way this typically works today, sort of the baseline system that emulates the safety systems you'd see in a production environment, is the robot is freed from its cage, but there's essentially sensing. There's a light curtain. And when the person crosses the region into that shared space where the robot works, the robot stops. This enables safety. A person can access that space efficiently, or effectively, but not efficiently. The person is working or the robot is working. And it can, it can result in not being able to make the business case for introducing these technologies. So now, alternatively, you might want to more effectively share space by enabling the person to get closer to the robot, to be able to sense where the person is in relation to the robot with a reactive system to be able to slow and stop as the person nears. That will allow the person to get closer to the robot safely, in this case, into the shared region. But you can see that does not necessarily imply efficiency. In this case, the robot is actually blocking the person's access to where they need to work. So they have to leave the space for the robot to continue, and then ultimately re-enter to do their work. So what we did was employ techniques for being able to predict where the person would be in space and time very early on in a trajectory, and then enable the robot to use that in its planning. So again, planning its trajectory, incorporating consideration of time. You can see here very early in the trajectory, the robot predicts that the person will be using that particular workstation. And the emergent behavior is that the robot falls back to make room for the person. So with these systems and other systems that we explored and developed in our lab, we were able to, through studies, demonstrate benefits of employing robot intelligence in this way. For example, we were able to see increases in concurrent motion between the person and the robot, reductions in robot idle time, and increases in distance between the person and the robot, which is a proxy for safety. So these results were counter to the prevailing thinking of the time that you have to trade safety for efficiency. But ultimately, when we look at Era 2, this is where I've spent the bulk of my career. When we look at Era 2 and we take a step back, ultimately these systems are really about getting out of the way. We are gaining a little bit in flexibility, but what else we're getting is just not enough. And that's part of the issue of low adoption. It's because use of even these systems is seen as zero-sum. So Era 3, this is the era I want to talk about. How do we break out of zero-sum and achieve positive sum? President Biden recently recognized the beginning of this new era in his infrastructure speech at Pittsburgh.
The work is made possible by funding from the Commerce Department. And they partner with engineers and researchers from Carnegie Mellon University who design the next generation of advanced manufacturing equipment, creating technologies that work alongside workers instead of replacing the workers. In fact, Carnegie Mellon and the AFL-CIO are teaming up to make these technologies, make sure they're designed to support workers.
So it's really outstanding to have this elevated to the national discourse and our set of priorities in this ways. So now the question is, how do we make good on this? That brings me to the central question. What exactly does it mean to work alongside, to support, and to augment? What are we trying to achieve with this? And what's our objective measure for success? Asking this is imperative because the answers frame the success criteria for the technologies that we develop. One of the takeaways should be that we're not innovating responsibly by guessing at the answers as to why automation and robotics can be good or can be bad. We need to understand the problem that we're trying to address in order to be able to solve it. And the problem is not necessarily that robots are taking jobs. We have decisions that we make regarding technologies, their design, their integration, and how we value them or make the business case for them. And these choices affect productivity, quality, safety, and other important considerations. But there are other considerations too. So we learned about additional objectives and drivers for automation in our extensive field work as a part of the task force. These involved interviews of 44 manufacturing companies across Ohio, Massachusetts, Arizona, 10 large multinational corporations, 34 small and medium enterprises, leaders in 21 industrial ecosystems, trade associations, community colleges, unions, manufacturing extension partnership offices. And Chris Fourier and Lindsay Sandeman from my lab spearheaded the 9 interviews and site visits of manufacturers across Europe, manufacturers, OEMs, suppliers, many that identified as having world-class advanced manufacturing systems. And what we heard was the importance of engineering for skills and training, for flexibility and low switching costs, and for economic opportunity for workers. We've seen how when we optimize for the traditional considerations, there are few applications that are limited to larger firms in certain sectors, and we see concentrated benefits for those technologies. However, we look to solve for challenges in skills and training, flexibility, and economic opportunity. There are many applications for automation and the potential for widespread benefits to both workers and firms. The dominant paradigm today is that an automation engineer translates the specifications of a domain expert into a robot program. We heard over and over again the need to better leverage domain expertise. We heard worker-centered approaches resulted in the most impressive and successful applications. However, by design, line workers with domain expertise do not have the technical skills to program robots. We heard that to change the equation, we need to be able to program the task and not the robot. This requires designing for workforce challenges too, and making decisions as to whether programming is intended to be done by technicians without robotics and programming expertise, or by engineers who are scarce in many small and medium firms. We heard about the importance of engineering for flexibility. the cost of the technology is only a fraction of its total integration cost. Integration is often performed by a third party, so there are very large costs to small changes going back out to this third-party firm. It limits productivity. It poses a high barrier to entry, especially for the small and medium firms that we're so concerned about. You might ask, do collaborative robots change the equation here? So not at all. Studies highlight that some of the greatest difficulties of using easy-to-use systems, in this case, such as Baxter, were that even if the robot itself was easy to program, it had to be integrated within a programmable logic controller, for example, as something as simple as receiving a signal of stock that's ready to feed. So flexibility to change robot programs and tasking, reducing switching costs is critical to overcoming the integration costs. Small and medium firms are locked out today, and we need avenues for introducing technologies that don't lock them out. That leads us to measurement, how we value technology and make the business case for investing in it. So what's still missing here is the worker. That means organizing your decisions to make economic opportunities for workers in a firm. You can translate this to wages of employees in a firm. When we upskill, we provide new training opportunities that translates into increased opportunities for workers and higher wages. A technician that receives training acquires new skills and will see a benefit in terms of wages in a firm. Similarly, a firm that provides increased economic opportunity for workers by providing higher skilled jobs, such as more jobs for engineers, which have higher wages, also creates economic opportunity. Interestingly, we heard that views on how technology was valued were changing. The traditional labor displacement calculation for making the business case for the introduction of a technology is increasingly viewed as outdated. And the benefits of collaborative robots are instead seen in augmenting and assisting rather than replacing. So we as technologists in academia and industry, we make decisions that affect our ability to achieve these objectives. We make design decisions that impact how easy or hard it is for a robot to be programmed. We make decisions about how hard or easy it is for these systems to be integrated. And we design for particular objectives and ways that we measure success. So that brings us back to the question, what should we be optimizing for, and what does success look like? Is it the traditional metrics of productivity, quality, safety? What if instead we solved for skills and training, for flexibility, for economic opportunity? So here's what positive sum looks like. It's a win-win-win-win. Is this possible, and what role does technology play in achieving this future? So I'm going to outline 3 technical challenges in enabling this new era. First, we need to be able to address the challenges around who is able to design the task and the robot program. Second, who integrates and configures it. And third, who does the robot work for? In other words, how do we measure success? I'm going to show that these challenges are solvable and that by solving them, we can change the equation and break out of zero sum. While much of this talk is focused on manufacturing, because that's where the data is, I want to emphasize that these challenges were raised in the bottom-up research on manufacturing, but we also saw the same challenges across other sectors and a variety of different approaches to automation in firms, from looking at everything from back office automation to automation in healthcare. These challenges are not just central to the future of work in manufacturing, but to many other areas where we're introducing automation, whether it be AI or robots. So the first question is, who designs the task in the robot program? There's options here as to who designs the task in the robot program, and there's trade-offs. So on 2 ends of the spectrum, we see a variety of approaches that firms are taking. One is low code. The other, on the other end of the spectrum, is high code. So the low code approach is a firm making the decision to bring in a technology that's aimed to be designed for minimal programming expertise. The idea is to let the technician or the office worker configure and operate the automation. And that makes sense because they're the ones with the best knowledge of the process. It makes sense to aim to empower them to use the automation. Many firms will say they envision a scenario where a technician shifts from a role of doing the task manually to operating the automation, and eventually the firm will be able to lever the worker's time and attention to operate multiple systems. Alternatively, in the high code approach, the firm aims to roll out automation that's highly configurable. Engineers take on this job of rolling it out. They experiment. They can re-engineer the process to make maximum use of the automation's capability. Ultimately, firms envision that this approach leads to reduced reliance on the need for technicians. So when we compare these head-to-head, the high-code approach is seen as offering the better chances of the biggest productivity gains because of the potential for extensive re-engineering of the process. In contrast, the productivity gains of low code may be more marginal. Think of the old adage, if you automate a broken process, you end up with a broken process. So now low code requires less in terms of skills and training, so it's possible for technicians to undertake. And the incremental training of technicians results in increased wages and economic opportunities for them. In contrast, the high code approach requires extensive skills and training in that engineers are doing the work. But it may also afford more economic opportunity overall because engineers have higher wages than technicians. So note that whether we go low code or high code, it doesn't necessarily constrain flexibility or how easy it is to modify or adapt the programs. That depends very much on the integration decisions that we'll come to in a few minutes. So there's no simple solution here. There are trade-offs, there are pros and cons for each firm to wrestle with based on their particular context. Now let's look at how technology can change the equation. Let's look at what are the challenges of these low-code solutions for programming robots. What makes them challenging to work in practice? And I want to show you that these challenges are solvable, and technology can change the calculus here. Let's look at the paradigm where we're aiming to enable a person to program the task and not the robot. The ideal situation is that we have a person that teaches the robot how to do the task, gives it one demonstration. So in this case, leveraging work from Nadia Figueroa Fernandez, Aude Ballard, learning a dynamical systems controller with local reactive constraints. You're aiming to give one demonstration for scooping up material from one receptacle to another while maintaining particular orientation to not spill the beads. Now, that would be the ideal, but that's not going to be sufficient because there's sort of task level information that matters here. So if the robot encounters a disturbance or is perturbed and is compromised from achieving the task, it's not able to recover, to be able to react to that and continue on to successful completion of the task. So we would like the person, the non-robotics expert, to be able to provide high-level information about what it means to successfully complete the task. We can do this via natural language to be able to compute continuous controllers that meet reactive task specifications. And we can also learn these types of temporal logic specifications from demonstration, leveraging the work of Hadas Kazit, as well as Ankit Shah. So bringing these technologies together gets us far. So the robot is able to complete the task. If for some reason it fails in completing that task, it can detect that and it can continue on to produce a plan that ultimately meets those high-level task specifications provided in, say, natural language form or by demonstration. Now, the devil is in the details. So from one demonstration, you're very likely to encounter something out of distribution at execution. And in this case, there's a particular portion in that configuration space I just showed you. And if the robot is perturbed there, it will not succeed in completing the task. Reactive task level response does not help you. It'll just end up in live lock, continuing to try to execute the task. And so we need something in addition. We need a paradigm that's different than a robotics engineer going back, inspecting the control policy, making changes, and then pushing it to production. Intelligent machine assistance, the ability to online learn and refine policies from these mistakes can make a difference. So in this case, the robot is perturbed to that particular part of the configuration space. It fails, it drops its marbles. It detects that via the task level program. It tries again. And this time, when it's perturbed to that same place, it's able to continue on. The control policy has been pruned, and the control policy has been modulated to ensure success after just one failure from this encounter. So these types of technologies brought together can enable easy demonstration, easy natural language instruction, to produce both motion level and task level reactive and robust execution. Now, we also have other pioneering work that's very exciting outside of this particular line of research. I'm thinking of the work of Doris Sadiq, of Matthew Gambale, developing technologies that can learn from a variety of human inputs and feedback, that can learn high quality, can learn from both high quality and suboptimal demonstrations, and that are able to learn robot control policies that are interpretable without sacrificing robot performance. Exciting technologies are beginning to escape the lab as well. I've long followed the work from the Mass Robotics Startup Cluster in Massachusetts, the work of Southie Autonomy, which is really an exemplar in pushing the boundaries of very low-code solution, quote-unquote, no-code solutions with really great results. So we have companies, we have startups pushing what's possible. We have impactful technologies from the lab that are poised to change the equation as to who has access to robots and what can be accomplished. Now, how exactly does this change the equation? Let's go back to our table of trades of low code versus high code as it stands today. Let's look at how technologies make a difference. Machines that leverage one or very few demonstrations and task-level instructions and can refine their controllers on the fly as errors occur can make a difference. These technologies enable worker-driven innovation. They make tasking of robots as easy as tasking another person. And they open up the possibility for experimentation by technicians for process re-engineering. This makes for increased flexibility, and it opens the doors to increased benefits and productivity driven by the technician. Next, let's talk about decisions that are made in integrating these technologies. Again, there are options as to who integrates, and there are trade-offs. On two ends of the spectrum, we have what we call top-down and bottom-up integration approaches. Top-down integration of automation is driven by senior leadership, and the company will bring in a third party or a third-party firm or consultant to make the automation work. It's a big investment for the firm, and there's big motivation to find gains in productivity. On the other side, we see bottom-up approaches. Here, workers are empowered to be the grassroots champions of the technologies, which makes sense because they're the ones that know the intricacies of the tasks to figure out what should be automated. The concern here is that workers bite off small projects for automation, nothing too ambitious. So the opportunities you'd see if you drastically reorganized your work or re-engineered it for the capabilities of the technology are potentially missed. So when we lay this out, top-down has gains in productivity, but bringing in a third party drastically reduces your flexibility. Now the firm has to go out to this third party or consultant every time they have a change they want to make. Workers in the firm are not gaining because they're receiving minimal training in the technology, since a third party will essentially be on call, and that results in decreased economic opportunity for workers in the firm. The bottom-up approach provides increased flexibility, since workers are trained and empowered to roll out the automation, but it involves a significant investment in skills and training. The upside is that it also translates into higher wages for those workers in the firm. So pros and cons. But the situation gets worse. So you remember we heard from manufacturers about the difficulties of programming the robot, but also programming the cell. We also heard that the promise of collaborative robots and these next generation technologies was in better integrating the technologies with human work. So for Era 3 robotics to be successful, we need to tackle additional integration challenges, and that's programming for collaboration. So an ethnographic study of the introduction of Baxter, conducted by Bilge Mutlu and Alison Soppe, emphasizes this point. So here are some select quotes from the interviews with the workers. He, the robot, just had a hard time doing work a lot, especially when he goes down. I'm like, what's up? Feels like babysitting my grandkids. Sometimes I write down on my timesheet, Baxter was not a team player today. I started working here long after the robot got here, and sometimes I have no clue what to do to fix him. Him helping would be good. So let's look at the technology challenges of enabling sort of deeper integration of these robots. What makes it challenging to work in practice? And I'm going to aim to show you that these challenges are solvable. So we remember from our prior example how confusing it can be to teach a robot to even just scoop with a demonstration. You watch it, so something's perturbed, something's a little different in execution. Sometimes the robot does it, sometimes the robot doesn't. It's a total mystery without a robotics expert inspecting the learned controller. Here's another example from the lab that puzzled us. We developed a dynamical systems controller to reach on both sides of the table, maneuvering around this sort of overhanging obstacle. So why in the world can it only manage to reach objects on one side of the table when the other side of the table should be equally easy? Even worse, these are the lucky cases where we identify the problem before deployment, and finding all the relevant failure modes is like finding a needle in a haystack. So the opportunity here is in developing intelligent machine assistance for integration and test to reduce the reliance on a human expert with deep knowledge and expertise in the automation. There are a number of exciting recent works that show this can be possible. So last year, Stefanos Nikolaidis, faculty at USC, presented a novel approach to simulate scenarios that can reveal failures in an HRI system. He developed a novel set of techniques for efficiently searching the high-dimensional scenario space to identify a diverse set of scenarios that span the quality metrics that a designer cares about. The approach is called quality diversity optimization and can help identify these types of problematic situations before they arise. We also need techniques that empower the worker to directly interrogate and investigate a model in a goal-directed fashion. So a technique called ROCUS, Robot Controller Understanding via Sampling, presented last year, enables exactly this. So students Yulun Zhu, Serena Booth, and postdoc Nadia Figueroa Fernandez, now faculty at UPenn, developed a tractable Bayesian approach to be able to find environments that result in a behavior of interest. So for example, the user can query for environments where the robot has minimal obstacle clearance to inspect. And of course, there are a whole host of other behaviors that would be important. For example, to assess legibility, or how sort of direct or how much a particular robot's motion deviates from a straight line. Any metric can be employed as long as it's computed as a value over a trajectory with this technique. So with this technique, we were able to quickly identify that the reason the robot wasn't able to reach to the right side of the table was because of an asymmetry in the kinematic chain and the difficulty of maintaining the required obstacle clearance when reaching to the right. A small modification to the allowable obstacle clearance enabled the robot to reach to both sides of the table. Finally, when you uncover a problem during execution, you'd like to be able to fix it right then and there. And many of the challenges are not just with the robot program, but programming the interdependencies between the robot, people, and other machines. So the ideal scenario is to fix up the robot, again, right then and there. And with techniques developed by Bilge Mutlu at University of Wisconsin-Madison and his team, he enables this type of situated live programming for human-robot collaboration, where a worker can set up and update trigger action programs on the fly while reconciling competing priorities for tasking. And their human studies show that this technique provides workers greater flexibility in experimenting with programs that require interdependent work between a person and a robot. So here's our table of trades between top-down and bottom-up as it stands today. Machines that assist in integration and test, machines that provide new flexibility for programming for collaboration, provide greater opportunities for technicians without extensive training to experiment and re-engineer their processes to find bigger gains in productivity. And these technologies can change the equation, move us beyond our zero-sum trade-offs. They can make bottom-up approaches a dominating solution. Lastly, let's talk about who the robot works for. What we optimize for pushes us to different technology decisions. Let's look at the traditional objective of optimizing for productivity. Based on the trades we've discussed, the way things stand today, this pushes firms to high-code top-down approaches for the introduction of their automation. And in fact, that's the dominant approach today. But what we trade is flexibility and economic opportunity for workers in the firm. What if instead the primary challenge for a firm is their workforce, and so that's what they're solving for? What if the firm were to optimize for incremental skills and training when trying to bring in new technologies? Based on the trades we've discussed, this approach constrains productivity and economic opportunity. So now finally, what if instead we did something different? What if we were to optimize for flexibility and economic opportunity? These objectives are of particular value for workers, but also for the firm. In our interviews and site visits, we asked, why are you introducing technology? What is your ultimate goal here? Are you headed to a lights-out factory? Is that what you're aiming to achieve in the long run? Where do you see all this going? We heard a variety of responses. Some said, yes, we're headed to a lights-out factory. Others said no. And here's the quote of one of the interviewees. He said, "Why would I want a lights-out factory? A factory without people is a factory not innovating. It's humans that drive innovation." So what does it look like if instead we aim to optimize for flexibility and human potential? What would it look like to employ the technologies that we've discussed here? So I'm going to illustrate this with a task, an experiment task that we've utilized in the lab, in which a person and robot are aiming to work together to prepare lunch trays. The person prepares sandwiches, the robot prepares drinks on a set of 4 trays. The person comes in, demonstrates their aspect of the work. The robot learns their priorities and preferences for how they move through the space, how they accomplish the work, their motions, their timing. The person then teaches the robot how to do the task via a few demonstrations, the motions of how to successfully pour the drink. Via programming for interdependence, live situated action programming, the person can easily specify, please do not work at the same station that I'm working at, maintain a particular obstacle clearance away from me. And if you're uncertain about what I'm doing so that we can easily coordinate, please communicate with me. So I'm now going to show you a video that utilizes some of these technologies to enable a person to work with a robot in completing this task. We conducted large-scale experiments led by Vaibhav Anhilkar. This was a part of his PhD, and Shen Li, in which people came into the lab. Via few interactions, they taught the robot how they wanted to complete the task. The robot used predictive models and a model for interdependent collaboration to be able to plan online where it would move and maneuver around the person, and to be able to communicate to complete the task.
Hey teammate, let's make some meals. I will pour juice. Please make and wrap the sandwiches. Let's start.
So at the start, the robot is highly uncertain where the person's going to go.
Please make the next sandwich at 2.
And so the robot communicates to reduce uncertainty. The robot is planning online with the PalmDP with an update rate of 0.3 seconds. And so every 0.3 seconds, it's making trajectory level decisions on how it moves through the space around the person. It's maintaining a belief over where the person will be in the space into the future. If it's highly uncertain as to what the person does, it explicitly directs the person, makes a suggestion for what the person should do. If it's somewhat uncertain, it provides a status update about what it's going to do, so the person can incorporate that into their own action planning. So in other words, it's making a decision every 0.3 seconds whether to communicate. So you can see how through much of this interaction, the robot is maintaining a strong belief over where the person will be and how it should move and respond.
I am pouring juice at 3.
In that case, though, it was somewhat uncertain where the person would go, so it provided an update about what it was going to do, so the person could use that in their own planning.
I am pouring juice at 4. I am pouring juice at 4.
And you can see in this case, after the first communication, the robot was still somewhat uncertain as to what the person would do, so it repeated the communication. It gives you a sense of, through this interaction, how smoothly it's going in terms of being able to maintain a strong belief over what the person is going to do to be able to collaborate effectively with them.
I finished pouring juice.
So now I know what you're thinking. You're thinking, Julie, we all know the difference between a demo in a lab and something that works in production, and there's a very big gap. Well, what I'll tell you is that these technologies are not as far off as you would think, and we have the ability to harden them. And I'd encourage you to come to the opening of MIT's new museum in October, because this demonstration and a set of these technologies will be available as a part of an exhibit for museum goers to come, teach the robots the motions of how to perform a task, like preparing sandwiches or setting a dinner table, be able to interact through demonstration to teach the robot the logical specifications of, for example, what it means to set a dinner table, and then to be able to collaborate in this way to share space and coordinate via communication. And so I invite you to Boston in the October timeframe. So I admit that positive sum seems idealistic. So in the real world, there are trade-offs, but I'm inspired by the idea that we've done this before. We've optimized for flexibility. We've done it within hard existing constraints. We've made automation that's designed for making teams better at performing tasks in uncertain conditions. Landing on the moon was certainly a complex problem, one that neither human nor machine could do alone. In a seminal paper from the 1960s titled The Role of Men and Instruments in Control and Guidance Systems for Spacecraft, designers of the Apollo guidance computer debated how these technologies should be employed, not to replace astronauts, but automation as the key to achieving something currently unachievable. We got to the moon by designing for the human-machine system and by considering the unique value and role that humans bring. With this framing, Draper, Whittaker, and Young traced the evolution of flight systems from the early aircraft in which the pilot served as the manual control, the manual information acquisition system, and then ultimately to deliver mail across the Midwest, the manual navigation system, to one in which, in the 1960s, new fly-by-wire technology was being introduced to augment the pilot's both sensing and power in flight. Then the paper proposed what was then a radical way to enable a computation and automation architecture that could be harnessed to support humans, astronauts, supported by ground control, to be able to overcome the uncertain and challenging events that were inevitable on a lunar mission. Our lunar landings were successful because the design focus went beyond the underlying technology to be able to create systems that enable humans and machines to seamlessly collaborate at the right times in the right ways. Beyond quality, beyond labor, the purpose of automation is to make human teams better at performing tasks. As we introduce automation, designing for the human becomes more central, not less central to achieving our goals, and more challenging too. Automation does not ever cleanly supplant humans. It changes the nature of work and the human's role, whether we design it with these intentions or not. But great successes, a moonshot, can be achieved if we design with forethought to these considerations. So here's our positive sum moonshot. What if instead of designing for the typical constraints, we design for flexibility, or we design for maximizing human potential? What if we aim to create technologies that are not indifferent to our humanity, but the ones that we design for worker opportunity and dignity? People feel that opportunity is decreasing, that the global economy is becoming less equitable. Robots are not driving this. It's convenient to say that they're driving it. It's convenient to blame them, but robots are not driving it. They can be a part of the solution, and ultimately, that's our choice. Thank you. Sounds good.
All right, sorry, on-the-fly choreography. Thank you so much, Julie. That was a fascinating talk and really has us thinking about the potential for robots and humans working together in the future. I think we should give Julie another round of applause. So for the question and answer, we have 2 microphones. There's one here in the aisle and another one, now I know why you were squinting yesterday. Apparently there's one over here too. So if you would please just come to the microphone. We also have online viewers, so I'll be monitoring the chat. And I'm just going to point to people to ask questions. So let's start over here.
Okay. Hi. That was a fascinating talk. I was really inspired. Thank you for that. And I've been following your work for a really long time now. So one of the questions, since even I work with collaborative robots in human-robot interaction, the same field, one of the issues even I come across every day is that cobots by design are built to be a little slow for safety reasons. So if they are working as a team with a human, it can never be, at least with the current technology, as dexterous and as fast as a human. So how do they become an effective team member then? If the human has to wait for a few seconds to coordinate with the robot, then how can they be an effective team member?
Yeah, that's a great question. So we also do hear that one of the significant limitations for that type of highly interdependent work, that type of responsive collaboration, is that the robot is not able to sort of keep pace with the cadence of a person. The vast majority of uses of collaborative robots today are not in that form of work, but are actually just enabling the robot to do work that's situated close to a person, but doesn't come with the structure, the rigidity of requiring cages around that robot. And what I'd like to emphasize is that while there are many possibilities I see in the future for that more responsive collaboration, there's a huge world of tasks and settings in which we need to be able to translate the domain expertise, the knowledge of how one person would tell another person how their work needs to change, to be able to make better use of these systems even in environments that you would typically call them coexistence environments. And that is a form of collaboration, that sort of shared representation and information exchange to translate the information that a person has of how to do the work to a robot. I don't think it's, there are some settings, if we could address that it would really open up a lot of possibility for this more type of responsive or interdependent collaboration. But one of the reasons we don't see those applications is because we still have a lot of work to do to enabling the more seamless collaboration, even just to making these systems more capable in what we would call maybe even a coexistence paradigm.
Thank you. That answer.
Let's go to the other side of the room. Can we have the microphone Check over here. I just want to make sure we can hear
Can you hear me?
Yeah.
All right, there we go. Yeah, I'm Kaluk Jakala. Your talk was fantastic, and I was really glad that you mentioned Bayesian learning. But deep learning and reinforcement learning are being used a lot more nowadays. And those methods are black box approaches, which make it very difficult to identify failure cases. Do you have any comments on that? Should we keep using these methods? Do you have another suggestion or an alternative to this?
Yeah. The advances and the excitement around it, I think, are well-founded and well-supported. One of the challenges is, I learned from a colleague, actually at one of the workshops on Monday, that in training up a technician, it would be typical that it would take 1 to 3 years to train a technician to do a job to a sufficient level that they could do it independently. Firms are investing in those long timelines in people, right? And so the question that, imagine the transfer of the domain expertise and knowledge and skills that's happening in that time frame. The idea that we're going to be able to sort of simulate in advance, and we're going to be able to encode in advance everything that system needs to know about how to do work in that way is a good goal to strive for, but it's also inevitable that we need to design better hooks for a person to be able to guide the learning sort of in situ. I think there's a really exciting work, some of which that I mentioned in the talk, about being able to learn more interpretable policies that don't sacrifice performance, and then that gives you the basis to being able to ask, well, how do we enable a person to be able to inject and guide and structure the system's learning in a way that really matters in that very specific context, in that very specific firm, for that very specific work. And so I think it's an enormously exciting research direction, but one that we need to invest further in.
Thank you, Dr. Shah.
Over here.
Hi, thank you so much, Professor Shah. I'm Anne Collin from Motional. I came out of curiosity and I got so much out of it. I think I'm speaking in the name of many of my coworkers. Thank you so much also for cutting through the noise that might be existing around this conversation in the public discourse. And so this prompts my next question, which is, which policy interventions do you think would make this transition easier or make our work easier?
That's really great. So, it's also really important to take away that technology is not the sole solution to these challenges. And my goal in this talk was to discuss the role that technology does play, because it does play a role. And oftentimes, our colleagues in the social sciences, their job is basically to understand the implications of the technology that we develop, as if it's just a thing that exists, right? But we know we shape it. And one of the really exciting directions and opportunities is to work collaboratively with social scientists, not for them to study our implications kind of post hoc, but to be able to work with them to drive the requirements that can make a difference in how we're designing. You leverage that scholarship and input as inputs into our technology creation and development. But that being said, technology alone will not fix these issues. And as a part of the task force, there was a very broad look at sort of organizational factors, policy dimensions. I know work that came out of that task force was the role that government contracts play in providing small firms the stability to be able, and the resources to be able to invest in new technologies and to upgrade. And so there are policy implications and decisions that also can really change this. But ultimately, even with that, we have limitations in the technology we are putting out, that we are enabling, that are really integral to many of these problems and challenges.
Thank you so much.
So I'd like to take one of our questions from online. So the question is, what are your thoughts on the role of compliance and intentional physical interactions for collaboration, the same way that humans do not always consider other humans as obstacles, but can push and nudge during interactions in close quarters?
Yes. So a key part of removing that cage, unless you're going to put the light curtain up, is expecting to some degree that there will be some physical contact and doing what you can in a work environment, in a workplace, to ensure safety with the use of that technology. There's various ways to do that. So, very, very light payloads, for example, the sort of dominant solutions we see in collaborative robots today do provide you a basis on which to be able to make decisions that introduction of those robots is safe for contact. But it comes with steep limitations, for example, in payload capability and speed, and pushing the envelope of what we could do in safe interaction can be a good direction to be able to change some of those other elements of the equation that make that reactive collaboration less desirable today.
Great. All right, we'll go back over here for a question.
Hi. Yeah, my name is Prashant Doshi, University of Georgia Think Lab. So I have a two-part question. My first question is that it seems like your team has visited many factory floors and looked at many different tasks. So I was wondering whether has your team truly come across tasks where the human and the robots are working side by side, and where the robot is truly augmenting the human capability? So that's question one. And question two is, what metrics should researchers use to show that the robot is truly augmenting human capabilities?
That's great. So yes, there are examples of effective use of collaborative robots, both in the coexistence paradigm and also in the responsive collaboration paradigm. They do exist. They exist in a variety of the firms. The large firms that are able to make significant R&D investments and mature these technologies, but even in what count as small and medium firms, there are these successes. There are these exemplars that have been successful at not just introducing one robot, but even introducing more. And there's a lot of opportunity to study these exemplars who have been so successful, and to be able to expand on what's made that so. In terms of how we measure our success, I think a key part of this is, and Ayana yesterday mentioned the draft report from the National Academies on Responsible Research in Computing. It highlights sort of a few things. One is how critically important it is to engage social scientists in your research, and also to broaden the notion of stakeholders as a part of your research. And although this work predates by many years that National Academies report that's now out for comment, I think it shows what can be achieved by building these collaborations early on in a research program or a new technology development, to be able to ask the questions of what does it mean to assess success, and then to expand the notion of stakeholders. It's not just delivering value, for a particular customer, but how can we expand the notion of who we're delivering value for, and what does that mean for us in terms of the technologies we develop. I'd recommend as a concrete, for those working on these types of technologies, as a concrete additional metric, is to look as deeply into the skills and training, ease of use, ability for people to come in and pursue a variety of flexible approaches to accomplishing the same task as one of the studies I mentioned pursued.
Thank you.
So I'm getting the eye from the program chair. So I would like to thank Julie once again. Thank you for the engaging questions. And it is now my job to send us off for the rest of the exciting program that we have in store for today. Thank you for coming this morning. Let's thank Julie one more time.
Thank you so much.